Let's start. What I'm going to do is I'm going to talk about point charges and what you can find using point charges. I'm really going to do kind of a repeat of the tutorial I did last year, but I'll change the numbers. Then I'll talk about what's fair game for parallel plates, what I can ask you with that, and then I'll take specific questions from the homework. So, what can you do with point charges? Well, first of all, I can give you a single point charge or two charges. Well, two charges to start out with. So here's two charges, just to make up different numbers from last year. Instead of 2 meters, I'm going to make it 1.8 meters. What could I find? Well, first of all, I could ask you to find the force between them. How do I find the force between point charges? You may or may not, you might, you definitely want your formula sheet out in front of you, because half the battle is which equation do I use when. As usual, I'm going to go fast. If you stick around till the end, I'll print this up for you. I'll also email it out to you as an attachment in about an hour, whenever the tutorial is done as well, once I've uploaded the video. Find the force. How do I find the force between point charges? To be honest, that would work if I happened to know the electric field at that location and the point at that location. I don't. So Ty, you're right. K Q1 Q2 over R squared. K is, Ty? A really nice constant compared to some of the other ones we've been dealing with. There's only one that's cooler than that, which we'll learn in magnetism. It's more complicated, but it is cooler because it has the best name ever. It's called the permeability of free space, which when you go home, Ty, what did you learn in school today? Mummy, I learned the permeability of free space. Oh, Ty, you are ever so clever. That's just the best name in my mind. If I was forming a rock band, we'd be called the permeability of free space. Isn't that a great name? Ty, what's charge 1? You know what? I probably won't write that. What will I write instead as a little symbol that replaces that? Okay, so be comfy with that, please. But 8 times 10 to the negative 6. What's charge 2? 6 or negative 6? Convince me. Forces and fields, the first line of your formula sheet. Final phrase, you said it. Forget the signs, right? So 6 times 10 to the negative 6 divided by 1.8 squared. Look up. Yeah, Colin, you too, look up. What would that be with no squared? That's potential energy, okay? Sadly, don't get them mixed up. Oh, but if it was potential energy, I would have put the negative in. I'm going to get 9 times 10 to the 9th. 8 times 10 to the negative 6, 6 times 10 to the negative 6 divided by 1.8 squared. And I get a force of 0.1333 newtons. I'll go 0.133 newtons. Direction. You know what? I can't give you the direction unless you tell me which charge you're referring to. So just for a thought experiment, what direction is the 8 microcoulomb charge feeling a force? To the left or to the right? Why? Like? Unlike? He's U in my block A. And he's U in my block H. Oh, you have? Okay. You better get those right. Okay? What else? I could have you find the electric, I will ask you to find an electric field at a location, either between two charges or to the right or to the left of two charges. In this situation, I'm going to tell you that location X is right there, and I'm going to say that this is 0.4 meters, and I want to find the electric field right there. How? I can't find the electric field from two charges at once. I go one at a time. There's a fancy phrase for that, Colin. We call it the principle of superposition. It means do one at a time and add them up vectorially. Vectorially. Or if it's a scalar, you can just add them up. Electric field, scalar or vector? Electric field, scalar or vector? Convince me. You know what would be also cool if it was on the first line of the formula sheet where all the force vector, forget this, I think. But yeah, I don't put a hat, I draw an arrow, but my arrow is hideous. By the way, as a lefty, that's really hard to do. Oh, this is what you guys do as righties. I should just flip my arrows and do them that way, but that'd be teaching it wrong. So I'm going to call this column charge 1. I'm going to call this charge 2. Fair enough? I'm going to find the electric field from charge 1. Symbol for electric field is E. By the way, if you saw that, that's probably energy, especially if there's a little P down there. I use PE for energy. Your formula sheet doesn't. How do I calculate electric field from a point charge? This is on your formula sheet. Yeah. So this will be KQ1 over R1 squared. Then I'm also going to find the electric field from charge 2, which is going to be KQ2 over R2 squared. K, 9 times 10 to the 9th. Charge 1, 8 microcoulombs. R1, 2.2, yes, all the way from here to here. 1.8 plus 0.4, 2.2 squared. Dope. Try that again. 9 times 10 to the 9th, 8 times 10 to the negative 6 divided by 2.2. And I get a yucky electric field, whatever, of 1,004. You know what? Since this is not my final answer, I'll go 5 sig figs. I'll go 14,876. 14,876 what? Units for electric field. Is there a way that you can get that right from the formula sheet? Yeah, the second equation. It says electric field is force over charge. Okay. Direction. How do I figure out the direction of electric field? I don't use like repel, unlike attract. I have to ask a question first. What's the question that I ask myself? Which way? Kyle, say it loud and proud. So I imagine a little plus there. How little? So little it doesn't have its own electric field, because that would change the question. Which way would a positive want to move because of this guy here? Now I use like repel, unlike attract. I say like repel to the. I repeat with charge 2, it's going to be 9 times 10 to the 9th. It's going to be 6, not negative, because forces and fields forget the signs. And it's going to be 0.4 squared. I'm going to be really lazy. Change the 8 to a 6. 0.4 squared. And I get 337,500 newtons per coulomb. Direction. Which way would a positive sitting right here want to move because of this guy? Attract. Left. If they were in the same direction, I'd go winner plus winner. These are not. I'll go winner minus loser. It's going to be this number minus 14,876. The net electric field is 322,000. Direction left. Okay. What else can I do with point charges? So same diagram, again, I made it 1.8 meters. I could have you find the potential at location X. Where is location X, Mr. Dewick? How about right there, where again, this distance is 0.4 meters. Okay. I could ask you to find the potential energy between the two charges. That would be K, Q1, Q2, just over R. In fact, you know what? I bet you I can do that by just backspacing on my calculator for a while. There it was, but just over R. There's the potential energy between. Oh, no. For potential energy, scalar, I would have included the negative sign. So between the two of them, they have negative 0.24 joules of potential energy. What does that mean? You know what? nothing that profound. I'm more interested in things like voltage and work. Is this asking me to find the potential energy? Kohei, do you see the word energy right there?
No.
Potential. You know what? This is asking me to find voltage at location X. How am I going to find voltage from a point charge? Can you find that equation on your formula sheet, please? That's the definition of voltage. That's not voltage from a point charge. Why can't that be from a point charge? If it's a point charge, what letter appeared in the bottom of your fractional equation always for a point charge? I went to go see a pirate movie the other day and I couldn't get it in because it was rated R. Tie. There it is. So you know what? This is my stupid wings for voltage. This is going to be the voltage from charge 1. Then I'm going to find the voltage from charge 2. And then I'm going to add them up. Tip to tail, scalars. Okay? I would have no problem, try that again. I would have no problem on your test giving you an electric field tip to tail. What would that diagram look like? There would be one charge right there, one charge right here, and location X would be there. You would have one electric field that was north-south, one electric field that was east-west, and you'd have to add them together tip to tail. But I will make them right-angled triangles. So it'll be Pythagoras and SOHCAHTOA. In fact, probably if I did that, I would only ask for either the magnitude of the electric field, which means, Mitchell, you could do the Pythagoras and quit. Or I'd ask for the direction, which means you could skip Pythagoras and just do shift tan or shift sine or shift cos and get the angle. I don't think I'd hit you up for both. Maybe, but whatever. I could also do that here. Who cares if they're at this angle? Because it's a scalar, you'd still just add them up. This question that I just sketched mathematically is going to be very similar to this question. Stop yawning, Ty. It's going to be 9 times 10 to the 9th all over 2.2, right? Oh, wait a minute. I missed the charge, Mr. Dewick. Ha. Times 8 times 10 to the negative 6 all over 2.2. I hope I haven't done that one before. The potential, the voltage from charge 1 is going to be 9 times 10 to the 9th times 8 times 10 to the negative 6 divided by 2.2. I get 32,727. I'll write that. 32727 volts. Direction is none. Scalar. Did I say scalar? Signs. 9 times 10 to the 9th. Negative 6 microcoulombs divided by 0.4. Negative 6 divided by 0.4. Once again, just to show you how alike these look, what would this be an equation for? Electric field. Oh, that's great. OneNote's restarting. I hope so. Let's see how much I lost. I will say OneNote is very stable. It crashes maybe once a year, and it has an auto save so that I never have to hit the save button. Pardon me?
You can back up recovery on your file.
It doesn't have that. As soon as you do anything, it's automatically saved. As I said, as soon as the only thing it didn't save, you know what? It even got the undo of the squared. So what did I get? Negative 135,000 volts. So what is the voltage at X? Add them up. Plus 32727. Okay, Clay, put your phone away again.
It's not even on my
You were on briefly there.
Well, yeah, when you were doing that.
Negative 102. I'll go to 3 sig figs, negative 102,000. What is the negative telling me? First of all, we call change in voltage potential difference. What is the negative telling me? You know what? I'm going to come back to that. What else can I do? Pause for 1 second. What else can I do? I can fix one charge in place, and I can move another charge around like this. So charge 1 is fixed in place, and charge 2 right now is heading this way at 5.2 times 10 to the 7th meters per second. North, east, south, west. Clay, what's this question you want me to find?
How far until it stops?
Mathematically, this is the same as doing and asking how high will it go. Throwing something up into the air, for those of you who are listening on YouTube. Mathematically, this is the same as throwing a ball into the air. You're giving it initial kinetic energy. As it's moving away, the Earth is pulling it down, is attracting it. As this charge is moving right, as this negative charge is moving right, the positive charge is attracting it. Yes? This is a change in height. This is a change in speed. You know what this is a job for? Conservation of energy. By the way, did I say how much work in this question? No, so don't go work equal. Conservation of energy. I would start out by saying KE initial plus PE initial equals KE final plus PE final. Clay, what did you say this question wanted me to find?
The distance it stops.
Then that must be, it stops, final KE is 0. Okay? Okay, this is going to be a half mv squared plus, why won't I write mgh? That's not what's moving this charge.
Why does it have initial potential energy?
Sorry?
Why does it have initial potential energy?
Is it starting out on the ground, or is it starting 2 meters high, metaphorically? So it's got some energy. Right? I mean, you can extend a lot of this and apply it very similarly to gravity, because the mathematics matches it very similarly. Okay? I'm just checking here. Can I use QV? I could if I knew the voltage between them. Do I know the voltage between them? Then, you know what? It's going to be okay. Now, I haven't given you the mass. In this question, I would have to say something like, assume Q2 has mass
1.67 times 10 to the negative 3.
There you go.
Oh, to negative 27.
well, you're making it a proton. I know this can't be a proton because its charge is too big. If it was a proton, the charge would be 1.6 times 10 to negative 19. And you know what? This has got some oomph to it. I'm going to go, how about, to the negative 10 kilograms. And then I go back, and I go do-dee-dee, and I go home. Where's my subscript button? I have that up here. Oh, it's up there. There we go. And I think if I do this, I can get it. There we go. Okay? So, you know what? This is several trillion protons, the 1.67, a bunch of them. How would I solve this? I'm not going to take this all the way. This is just to let you know how we can mix and match stuff. And I'm not even sure there's going to be one like this on your test. Maybe. I would get this as an answer. Find it. Crunch it. I would do each of them separately. I would go a half mv squared. Well, you know what? I can do that part pretty easily. It's going to be 0.5 times 1.67 times 10 to the negative, what did I say, 10? Times 5.2 times 10 to the 7th squared. There's a half mv squared. That's how much kinetic energy it has. 225,784. Plus whatever that is, and I would get an answer. How would I get R final by itself? I think I would multiply the R to the front. Yes? And divide this to there. I think R final would end up being K, Q1, Q2, all over whatever the heck that was right here. I've made up bad numbers. I did a quick rough guess in my head, and the answer is going to be stupid. So I'm not going to bother crunching it. Okay? I did a quick calculation. It's going to be a yucky answer. Point being, in that potential energy equation, I can find whatever I need. Probably, Jose, I'm going to ask you to find a speed, a v, which is a little easier to get by itself, although you will have to square root at the end. Is that a hand up? Yep.
What about R? Are we going to find an R?
We just did. That would be fair. Now that I've shown it to you, it would be fair game. Sure. It's a little yuckier to get by itself is all. That, yes? Did we, like this?
Yeah.
Okay. This is a much more realistic or better question. Jose, what's this asking me to find?
Force.
How much work to move the negative charge to location P? Okay. Work. Why can't I go force times distance? I could figure it out. It'd be K Q1 Q2 over R squared. Why can't I go force times distance? So? So?
Because you like to make it hard for us.
No.
Oh.
No. Folks, this only works if you have a...
When did you think of that?
Yeah, come on, say that.
This is, by the way, this is why for orbits we couldn't use force times distance to figure out how much work to get something into orbit, because as you leave Earth, what happens to the force of gravity?
Against reduce.
It's weaker. Changing force. We have to go with our bigger, our more universal definition of work. Same idea here. Force times distance is changing because the force is not constant. Now, between parallel plates, since the electric field is constant, the force is constant, I can go force times distance. That's why the parallel plate math was much shorter. But between point charges, by the way, Ty, you were sort of right. The reason the force isn't constant is because in the equation there's an R in the bottom and R is changing. And if R is changing, force is changing. So what's my other definition of work? Yeah, this one's not on your formula sheet. This is one of the few ones you've got to memorize. You know what? I think we're moving it from one location to the other. I think it's starting and ending at rest. What's changing anything? How am I going to find the PE final? Are you done? Could you hand it in the appropriate block for me? Thank you. How am I going to find the PE final? Which one? The whole point of this is you need to know which equation.
KQ1.
Yes. So it's going to be K Q1 Q2 over R final minus K Q1 Q2 over R initial. Am I going to put this negative into the equation or not?
No.
Am I going to put this negative in for Q2 or not?
Yes.
I've heard no, I've heard yes. Convince me.
That's because you didn't say it. It's clearly yes.
Vikas.
It's because you decide to
It's a scalar, signs. Okay? I'm going to put the negatives in. Are you guys okay doing the rest on your calculator? I mean, walk through this if you want, but you guys are dying right now. I'm seeing heads nodding. This will be 9 times 10 to the 9th, 8 times 10 to the negative 6, negative 6 times 10 to the negative 6 divided by, what's our final? Don't say 2. What's our final? How far apart? 4, right? 4 minus 9 times, you would get a minus minus here, which would give you a plus. I think you will get a positive answer. It will take work. Which way does this charge want to fall?
To the right.
It wants to fall to the right?
Towards the left.
Huh?
Towards the left.
Well, yeah, attract. So this is like lifting something up. It will take work. You will get a positive answer. Do you guys want me to crunch the numbers, or are you guys okay? You okay? Okay. Yeah. 9. Lots of typing. What else could I ask with point charges? Going back to here, I could ask you something like this. I need this diagram, Mr. Duick. You know what? Maybe I can use this diagram here. Sure. Copy. Let's go way to the bottom here. Oh, I can insert space, Mr. Duick. You forgot. I think you can. Hey, that worked. I could say, if, let's do our Q2, Q1. If Q1 is, let's make it a proton. So we'll cross that out. We'll make this positive. Okay? In fact, I'll even color it in. It's a proton. At rest, how fast will it be traveling if it is released? How fast will it be traveling at point P? How fast will it be traveling? Good gosh, Mr. Duick. Okay. This is like dropping an object, but in this case, I think charge 1, Q1, wants to fall up. Because like charges. Okay. This is a change in height, change in speed. Yucky, curvy force. This is a job for conservation of energy. I would start out going, oh. Okay. I would say, well, it does say starts out at rest. Yay! It's going to be K, Q1, Q2 over R initial, which would be 2, equals K, Q1, Q2 over R final plus a half mv final squared. And Jose, this sort of answers your question. Would you ever ask me to find R? I would have no problem giving you how fast it was traveling and saying, well, how far away has it gone? Get the RF by itself. It's a bit yucky, but it's doable. Yes?
Did you ask it for the mass?
Yeah, it's a proton, so no. It's a that's on your sheet. For a different charge, I doubt it. I've flogged that during the year. Okay? I would minus this to this side. I'll get K, Q1, Q2 over R initial minus K, Q1, Q2 over R final. That equals a half mv squared. I would crunch this and get an answer. Type, 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 get an answer. And then I would go times by 2, divide by the mass of a proton. My answer is going to be sitting right there. Square root, that equals V final. So I could do that. Or I could have, hey, have the proton coming in from a very long distance away. When I say a very long distance away, what do I really mean?
Infinity.
How much potential energy did I start with if I started out at infinity? I could have it come in at a certain speed. As it gets closer and closer and closer and closer, this, Jose, would be a fair game question. As it gets closer and closer and closer and closer to this proton, to this positive charge, what would the proton start to do? Speed up or slow down? This is pretty basic, folks. Positive charge, proton coming in. What can you tell me these like charges are going to do to each other? Repel. It's going to slow down, slow down, slow down, slow down. Eventually, for a split second, it'll come to a stop. I could say, when will it stop? Where will it stop? You're finding R final. V final is 0. Stopped. Oh, potential initial was 0 out at infinity. Find R. Okay? That would be fair game. Plate charges. Hey, if this charge Q is 3 electrons here, how much work to move it from the top to the bottom of the plates? Okay. Oh yeah, the electron would want to stay by the positive 600 because it's negative and that plate is positive. You would have to do work to move it down. This question wants me to find work. Okay, work is force times distance might work, no pun intended, but I would start here because between plates there is such a lovely equation for potential energy, or in this case, change in potential energy. What's the lovely equation for potential energy or change in potential energy between plates? Yep. Q times the change in voltage. In other words, Clay, the work is going to be the charge, 3 electrons, times the voltage that they traveled through. You'll notice I'm not even using this. I could, by the way, with that distance, go force times distance. I'll show you how to do it in a second. 600. By the way, the change in anything is what? So it should be 0 minus 600, which would be negative. Are we doing scalars? Electrons are also negative. Here's what I know. The charge does not want to move down. I would have to be lifting it. I would have to be pulling it. I would have to be doing work. I knew the answer was positive. Is that okay? Whatever the heck that works out to be. You want to do it with force times distance? It works. No pun intended. Clay, that distance there. Force. Which force, Clay? Look up. Electric force. What's an equation for electric force on your formula sheet? I can't use the one with the R in it. Is there another equation that has electric force? You're right. Get the F by itself, please. QE? Yes? Do I know Q? Negative 3 electrons. Oh, 3 electrons. That's positive. Do I know the distance? Yeah. Do I know the electric field? Be cool if there was an equation that I could find the electric field if I knew the voltage and the distance between them. Is there?
Yeah.
What? The voltage divided by the distance times the distance. Clay, is there a D on top?
Yeah.
Is there a D on the bottom?
Yep.
Do you know what this ends up simplifying to after 3 lines of work? The one that Kyle gave us out of his head. Does force times distance work here? Yep. Is Kyle's method significantly shorter? Yep. Knock yourself out. Okay. What else could I ask between plates? Hey, if the charge is an electron, find its speed when it hits the top plate. Mitchell, what does this want me to find? Did it say velocity or did it say speed? Probably a scalar. You know what? This is like dropping something. I can do this with conservation of energy. Now, Colin, is there a change in speed? Is there a change in height? That works. Is there a yucky curvy path? No longer works. And is there a yucky curvy force? No longer works. But you know what? I'm telling you, conservation of energy works. You could find the speed by using force equals mass times acceleration. You could find the force by using QE. You could find the acceleration. You could find the distance. VI is 0. You could find VF. Yeah, and it'll get you there. It's the same thing, by the way, as Clay walked in. You'll find towards the end, oh, stuff's canceling. I'm getting a nice equation. I could have got there quicker. I would go like this. I think we're starting at rest. When you drop something and it hits the ground, how much potential energy does it have left? When this hits the far side, how much potential energy does it have left? Now, it's electric potential energy, but I'm telling you, Dustin, mathematically, it's the same as it hitting the ground. Is that okay? A half mv squared. Kyle, how can I do potential energy between plates? Could also go force times distance, but you'll end up right there. This is the equation that has the V and the V in it. This is why I've started going to the wings. Hey, you want the speed? It's going to be 2 times Q times V divided by the mass. How do I get rid of a squared? Square rooted. Which mass? It's an electron. 9.11 times 10 to the negative 31. Which charge? It's an electron. 1.6 times 10 to the negative 16. What's the final mathematical step that we're doing to get the V by itself? You know what? Can I take the square root of a negative? You get an error. Put everything positive in there. I mean, yeah, the scalar. You know what? It's, again, I think the change in voltage is negative and Q is negative. It's positive. Colin. Yes?
Yes.
Starting at rest? Yes? Yes? Okay. How could I find the acceleration, Mr. Dewick? Well, electric force equals ma. How can I find the electric force? Q times E equals ma. Yes? How can I find the electric field between plates? Why, that's the change in voltage over the distance. That equals ma. How would I get the A by itself? And if I plug that in here, I'm going to get VF equals the square root of 2 and a D on the top. And the A gets replaced with a Q, a delta V, and an M and a D on the bottom. What do you notice happens to the D's? And, oh, are you saying, again, I get 2QV over M?
Well, I would probably solve for E separately.
But I'm telling you, what I'm proving to you is that method would work. Count with me. 1,
2, 3, 4, 5.
6, 7 if you solve for E separately. Count with me.
1, 2, 3.
I would drop my mic and walk off the stage. Just saying. Right? And you've had me long enough to know that I have a fondness for an efficient algorithm that gets me there cleanly. But yeah, force times distance will get you there. Only between plates. Why? Because the electric field is constant. That means the force is constant, and I can use force times distance. What if they ask for time or acceleration? You know what? We just walked through acceleration. You can use physics 11 since plates have constant force. You can use VF equals VI plus AT. Oh, you want T? You could go T equals VF minus VI over A. Or You could use d equals VIT plus a half AT squared. What was V? 0, and you can get the t by itself that way. All the physics 11 stuff can be pulled in here. This was, you might recall, I went on a nice rant about plates being mathematically nice. This is all part of that rant. They really are. Oh, and also television. Oh, and also it explains lightning. So parallel plates are kind of cool. An advanced question. Here's a proton with this much kinetic energy, and it's moving into a region of charged particles. The proton will be stopped momentarily in what region? What's your hint that you want to solve this with energies? What's an even more blatant hint that you want to solve this with energies, Raj? Because the question is talking about energies. Okay? So I would start out saying, you know what? This is a change in height, conservation of energy. Are any of these 0? Stopped. KE is going to be a half mv initial squared. Which m? It's a proton. Yes? Hey, Kyle, what's potential energy between plates? Which Q? It's a proton. You know what? Q, change in voltage, technically. So let's assume that we want its final to be, we want to know when it's going to stop. Okay? Maybe I want this to stay and I want this to be 0. I'll have to think about this for a second. Let me come back to it. You know what? I think actually I want to say right now, this is initial. Is it between the plates right now? Does it have any potential energy right now? It's moving at a constant speed. But as it travels through here, it's going to be going through a change in voltage. And I think what this question asked, it said, it will be momentarily stopped in what region? I'm going to solve for the change in voltage. If I get, for example, 117, Mitchell, that would be region L. If I get 228, that would be region M. If I get 397, that would be region N. I'll get the V by itself. How? Divide by Q. No need to square root. Okay? So, having said that, more point charges. By the way, this one here was from the homework. This was keeping a charge at rest. I don't think that's on your test. More point charges. How much work must be done to move a 5 microcoulomb charge from X to Y? What's this asking me to find, Vikas? Work, scalar or vector?
Scalar.
You know what? They're trying to scare me with that diagram. And to them I say, bring it on. Bring it on. You're not going to scare me. You tried to make a yucky diagram so I would panic. But it's a scalar. Are these point charges, Vikas? Then you know what? It's going to be the change in potential plus the change in kinetic. I can't use force times distance. Sorry, Colin. And it's going to be K Q1 Q2 over R initial. Over R final minus K Q1 Q2 over. Well, you know what? There's a better way. There's a better way. What's another way to calculate potential energy? I think I can go Q times the voltage at location Y minus Q times the voltage at location X, where this is Q. How would I find the voltage right here? Hey, we did a question like that already where I said find the potential difference between two charges. You would find the voltage from the first charge, voltage from the second charge, add them up. This question, Clay, you can actually take a bunch of shortcuts on because these two charges are identical and this distance is identical. You could actually just find the voltage and then times by 2. That would give you the voltage at X. Find this potential, this voltage, and then times it by 2. That would give you the voltage at Y, QVY minus QVX, and you're good to go. Okay. It looks like I have deflecting plates here. I'm guessing that was what somebody asked. Yeah, from the homework. I think we're okay. Now I'm going to do my usual, hey, questions from the homework. That was kind of a rundown of a bunch of stuff. Yeah.
Lesson 9, number 4.
Lesson 9, number 4. What was yours?
Mine's just a general question.
Yeah.
Does electric field always go from positive to
That's how, so I got to be fussy. Its direction is defined as from positive to negative. We have to define it.
How come when there's like an electron in the middle of the field, it's opposite?
So are you ready? If the electric field, ready, is this way, which way will an electron sitting right here want to move? Left. Why? Because an electric field is defined as which way a positive would want to move. Which way will a positive want to move? Look at the arrows. So which way will a negative want to move? Left. And so between plates, for example, if you have, this is charged, you know what? Let's even put numbers on here. 600 volts and 100 volts. Which plate is more positive?
600.
So which way would a positive want to move between them if it could?
From 100 to 600.
Which plate is more positive?
From 600 to 100.
The electric field would look like this. It would not look like that. If you did that, I'd be saying, why are the lines closer together right there? Why is the electric field stronger right there? So the lines would be parallel and pretty much equally spaced apart. There is some blurring on the edges. This is why even the best TVs could never get a great picture, by the way. A proton wants to move up because that's how electric field is defined. Which way would an electron want to move? Yep. Okay. So if you want to put an electron here, it's going to feel a force down. Oh, from the less positive to the more positive. Really, from what it sees as a negative to a positive, because as far as it's concerned, this is 500 volts and the top is 0 and the bottom is 500. Mathematically, it's the same.
Just like if the top is negative 100, it's 700.
Yep. Yep. That's why I think in the what block are you? You're block A. In my first circuitry lesson, I said, well, technically voltage is always a change, but we just get sloppy because it's always a change. Is that okay? You had a question, Clay? Sorry.
I just figured it out.
Oh, you just figured it out?
Yeah.
Okay. I figured you might if I waited. You're smarter than you look. Any other questions?
Thanks.
Pause, and I'll do my which questions I like.
I don't have my lunch right now.
Yeah, questions that I like from the review. I think I do ask you a question about electric field diagrams. So something like number 1, between plates, or if there's point charges. I can't remember whether I put plates or point charges, but there's going to be a question about how we symbolize, how we draw electric fields. Number 4, I'm not really that fond of, to be perfectly honest. 5. Sure, 6, direction of the electric field. Except number 6 is a circuit diagram. I take that back. The physics of having you find an electric field between plates is fair game, but I won't give you a circuit diagram. I'll clearly just label the plates with the voltages. Okay? 7, absolutely. Electric potential, voltage. Okay, so that's fair game. Oh, and 2 points and another location either in between them or to the left of them, or in this case, to the right of them. I love number 12. Electric field between 2 points, or again, tie, instead of between the 2 points, to the left or to the right. I just have to give you the appropriate distances so you can do the appropriate radiuses, radii. Magnitude and direction. How do I get the direction, Colin? Electric field is defined. Which way a positive would want to move it could. By the way, if I'm asking you to find a voltage, because scalar is signs, you better expect at least one of the charges will have a negative on it. That would just make sense to see if you picked up on that. Yes? 14, magnitude and direction of the electric field between 2 charges. In this case, to the right of 2 charges, but 2 charges. I like number 16, I like number 16, I like number 16. Okay. Faizan, what's number 16 asking me to find?
Final speed.
You know what? I would use conservation of energy. Can't use force times distance because the force is changing. Colin? An electron in this electric field will have an electric force acting on it in which direction?
Left.
In which direction?
West.
Yep. There you go. Okay. I like number 18 because potential, voltage, scalar, it just means add them up. Even though this diagram looks terrifying and you might be tempted to go tip to tail, it's going to be this voltage plus this voltage, add them up. No tip to tail. By the way, I'll bet you one of those answers is what you would get if you did do Pythagoras. I like number 20, I like number 20, I like number 20. How much work? So we did one where I found a speed between point charges. Here's how much work. Oh, and then part B says find the potential difference, the voltage. Yeah, sure, that works too. Oh, I like 21. So I told you there would be some kind of electric field diagram. How can I figure out, by the way, which one of these charges is positive? Which way do the arrows always point in electric field? From what to what?
Positive.
From positive to negative. In other words, I know B is wrong because the arrows are pointing towards the positive charge. And I also have to think about what the field would look like for equal but opposite charges. 22 I like, 22 I like. What's the maximum speed? This is just like dropping an object. I just told the people that came to my tutorial a secret. I gave them a hint about a question. Sorry for those of you that are enjoying the sunshine right now. Sucks to be you. Okay, here we go. 23 is great. Electric field and electric potential. Make sure you don't get them mixed up. One is KQ over R squared. One is KQ over R not squared. Don't get them mixed up. Uh, 24 is fair game in that it's asking how much work. The diagram looks yucky. No, it's a scalar. Don't freak out. I don't think I'm giving you that yucky a diagram on the written. I might feel comfy as a nasty multiple choice is all. 25, here's an electric field diagram. Which one of these is correct, by the way? Which shows the electric field near a negative charge? Sorry? You're right, I think, if you say it louder.
D.
D, because it points from positive to negative. .26 cathode ray tube, not on your test yet. Okay? So how a TV works, it will be on a later version of a test when we look at TV properly. In real life, actually, they stopped bending the electrons with parallel plates and they started bending them with magnets, because it turns out electrons also get bent by magnetic fields. That was one of the first hints that electromagnetism is one force. It is. Number 27 is electric field a vector? They are at angles. This would be fair game. In fact, I think there is one as a multiple choice question. Oh, no, this is asking you to find charge Q2. I take that back. This is a little overkill. Cathode ray tube, I'm not gonna test you on it. 30 is good. How much work? $32 is a little tricky. I'm not that fond of it. Look at my answer key and you should be able to figure it out. 33, sure. By the way, charge L, is charge L negative or is charge L positive? How do you know? How about this one here? Are you positive? I mean negative? Oh, yeah, okay. Both of these must be negative. Yes? That might be a nice way to do an electric field multiple choice question. 35, again, electric field with 2-point charges. You've seen like 8 of those. That's my way of telling you I guarantee it's on the test. And again, I'm either going to have you find the electric field between them, to the left of them, or to the right of them. On the written, they will be in a nice straight line, though. So you'll have to add them vectorially by going winner minus loser, but not going tip to tail. .36 electric field diagram. That's fair game. The net electric force on charge 2 from 3 charges. That's a little overkill. 38 is cathode ray tube. Not going to ask you that on the test. So 39, this is also fair game. This is exactly like dropping an object through plates. It's just that you're not starting at rest. So your KE initial is not 0. Okay, a little more number crunching. 40 is fair game, so electric field between plates. You know what, 41, this might be a nice way for me to get you to do a little bit of vector math without doing the math. I might say something like just which arrow best represents the direction of the net force. Something like this. Okay. Cathode ray tube 44, you can not worry about. .46, I'm not going to put one like this on your written, maybe as a nasty multiple choice, although it's not that nasty. It's a scalar. They're just trying to scare me. Kyle, what am I asking you to find in 47? Hey, I've been told you there's going to be one of those on, so yeah. 48 scholarship, no. 49 scholarship, no. See, 50, we actually did this finding the mass, but I'm not going to throw this at you on your test. It's cool. Not that hard, actually. 41, no. 51, nah. 52, nah. There you go. Let me pause the video.